Hello everybody and welcome to Calculus and Vectors. I know recently we just finished advanced functions, but sadly school doesn't wait and so we're off to the next course. The first chapter that we're going to be dealing with is actually rate of change. We've done some work on this last course, but as you might recall, I always told you that the way we do it is going to be different in calculus and vectors, so that is where this chapter comes in. You should be happy to know that the first way we're going to learn to find the average rate of change and the instantaneous rate of change is by actually using the slope of a curve. So what does that mean? Well, all that means is that we're coming back to our favorite tangents and our secants. Again, today, all we're going to do is go over the way we learned in advanced functions on how to calculate the AROC and the IROC of a graph or a function. As a brief summary, the average rate of change refers to the rate of change, of course, of a function over an interval. So how does this function change during a specific time or over a specific domain? Well, the way we figure this out is by finding the corresponding slope of a secant connecting the two endpoints of the interval. That might sound complicated, but a secant is simply a line that crosses the graph at 2 points, and those points are actually the beginning and end of the interval we have to find. Again, from grade 9, we learned that the slope of a line can be found using the slope formula, which was delta y over delta x, where y is the dependent variable and x is the independent variable. Recall that that triangle just means change in, so therefore delta y and delta x is just the change in y divided by change of x, and changes are simply the last value minus the first value, and so we get y2 minus y1 divided by x2 minus x1. Nobody's stopping you from writing y1 minus y2 divided by x1 minus x2, you just have to keep them together. So if you're writing 2 first for y, you have to write x2 first for the x's. You can't change them because that will probably produce the wrong answer. Again, if you're trying to find the units for the average rate of change, or any rate of change in general, you would simply express it as the units of the dependent variable per unit of the independent variable, which of course makes perfect sense because when we're doing delta y divided by delta x, if we keep track of the units, we're going to divide the units of y by the units of x. And so if we had time, for example, in kilometers and x in seconds, your final answer would be kilometers per second. Using this, I would actually like to show you an example of how we could apply the slope formula and also go over other things we learned last year about calculating the average rate of change. Okay, so here is my simple example for helping us remember what the rate of changes are. So for AROC, so average rate of change, we need an interval. For example, let's take the interval between -1 and 0. We actually have two values here that are perfectly whole. So we have -1 and 5 and 0 and 1. So we'd substitute those values in. Again, the order doesn't matter between choosing if this is x1 and this is x2, but you just need to keep them together. I like to start at my most left-hand side as x1. So my first x would be -1, and our y value would be 5, and our second x value would be 0, and our y value would be 1. Using this, we actually found that the slope is -4. So for every x, we go down -4 y values. In this case, it's -4 units. If we wanted to find a different interval, so for example, between -1 and 2, we would again just simply identify the points. Now the only thing that changes is that we have 2 and 5. Let's see what that gets us. So this is 2, and this is 5. So our average rate of change is 0. We actually didn't change because, as you can see, they're on the same line. So the slope of that line would be 0. It's a horizontal, which makes perfect sense. When it comes to talking about, for example, points like this, between between 0 and 1.111, for example, you could just substitute those values in. So you take this and you put, hey, 1.11, and this is 1.11. What does that get us? This is what it takes us for y2. If we substitute those in, we can actually find the slope. So again, that was 1.11. And so our answer is actually, there you go. So our answer is actually -0.7921. Does that make sense in the context of our graph? Let's see. Between -1 and 11, yep, it seems to be going downward. Therefore, our answer is correct. Again, if this was an actual graph with units, the way we would express this answer would be the units of y divided by the units of x. So you would say that the average rate of change per, for example, between 0 and 2, you'd figure out what the slope is, and then you'd say the units of this side, for example, were seconds, and this was kilometers, so you'd say kilometers per second. The other two things that you need to keep track of is, of course, figuring it out from a table. A table is probably the easiest one because you'll be given those intervals. You'll be given your x values, you'll be given your y values. You just need to know what you're looking for. So if it says between the first 10 seconds, that would be between 0 and 10. If it was between the last 20 seconds, you would take the last one and then minus 20. That would be your interval. The last way you need to know to figure out average rate of change is by using the equation, of course, and as I showed you before, you just substitute your values in for x and then use the formula to figure out the slope. Nothing here is exceptionally hard. We've actually done most of the work in grade 9, surprisingly, and in in advanced functions, we've gone over this many times. Now that we figure out how to find the average rate of change, let's find out how to find out the instantaneous rate of change. If you don't remember, the instantaneous rate of change refers to the rate of change at a specific point. So before we had an interval, and now we have a point. It corresponds to the slope of the tangent passing through a single point or the tangent point on the graph of a function. So now we have to keep track of what a secant is versus what a tangent is. If you forgot what a tangent is, it says it right there. It's just a line that passes through one point of a graph. The important thing you need to understand is that this point must be as close as possible to all the other points on the graph. So what do I mean by that? I'll explain it in the example, but if we have the point 1 and 5, you need to make sure that your line isn't going completely the other way from the point 0.9 and the point at at the point at 1.1. They need to be all in the same direction, essentially. Again, I'll explain this in the example. To estimate the instantaneous rate of change, you can actually calculate the average rate of change over a small interval for which there is data. So if you're given a graph, of course you can't zoom in like you can on Desmos, so you're going to be limited to the values you can actually read off the graph. If you're given a chart or like a data table, again, you're going to be limited to the data that was given to you. However, if you're given an equation, you can easily substitute a very small value into there that is super close to the point you're trying to find, and that way you'll actually get a fairly close estimate for what the tangent is, and therefore what the instantaneous rate of change for that point is. If you want another way to estimate the IROC, you could also use the slope of the tangent drawn on a graph. So instead of figuring out a point close to the graph, you could actually draw a line that intersects that point, and then you would figure out the two closest whole values that are part of that line and use those in the slope formula. Again, both the methods that I talked about are pretty limited by their accuracy because they all require you to use estimates, and some of them require you to draw, and depending on how steady and how well you can deal with a ruler, your answers are probably going to vary from classmate to classmate, which is not what we want in math. Either way, I will now show you an example on how to do instantaneous rate of change on a graphed function. So again, going back to our graph from the average rate of change, we could use it to actually find the instantaneous rate of change for certain points. So for example, what is the instantaneous rate of change at this vertex or this local maximum? Well, the way we would do this is by either making a line that goes through this point and then also follows the direction of the points around it. So what I mean by that is that you can't just make a line that goes straight down, right? This line that you make has to be close to the direction of what this point is here and what this point is here. And if you are smart enough, or I shouldn't say smart, but if you can figure it out, you'll actually have a horizontal line that goes through the point 0, 5. The way we could prove this is, of course, by using some very small value and then figuring out the average rate of change for a very small interval. Because as you can imagine, if we select a point that's over here, we're gonna have a diagonal line, right? If we select a point that is over here, we're gonna have a very small diagonal line that is formed. But if we keep zooming in, like as you can see here, the graph itself is becoming more and more linear. So at this point over here, it all looks like it's 5. So if we were to select a point, for example, there you go, 1.9999, Desmos is telling you that that point over there is 5. So then 5 minus 5 in our equation here would give us 0 as the slope. If we wanted to use another point to find the instantaneous rate of change for example, this point over here, 2.6, and we could substitute those in. So again, our first point is 2.6 and its corresponding y value. Oh no, I lost it. Give me a second. 3.704. 3.704. We would substitute a value that's very close to 2.6 into our graph. Again, the way you can do this, instead of like substituting right here, you can make a graph. And let's make it 5.99. What does that give us? 3.709. So 2.599 is 3.709. And so our answer is actually -5. Was that expected? Maybe not, but that is what we get as our instantaneous rate of change at the point of 2.66. If you wanted to make this even more precise, we could actually continue substituting those values in and look what we get. Oh, we got a 0. Does that make any sense for us? Let's see what happens if we keep zooming in. Can we actually get a different value besides 3.704? Perhaps yes, but perhaps no. That is the biggest problem of estimating. Because once you zoom in far enough, like you still can't tell the difference, but that difference is there. If we were to actually substitute that value into our equation, let's see what we get. We might get a very small difference in our answer. There you go. That's how small it was. Now, if we were to substitute that in for our value here, and then if we wanted to actually figure out what the value at 2.6 is, perhaps that was also rounded. That's something we need to keep track of. Nope, that was perfect. We actually get a value of negative 4.67952, which is definitely not 0. That is why we're actually going to learn a more advanced method of finding the instantaneous rate of change, which is again where calculus comes in to help us out. So I think that will be a very fun lesson, so hopefully you stay tuned for that. But the way we're going right now, all you need to know is that to find the instantaneous rate of change, you need to select a point that's very, very, very close to the point you're looking at, figure out what its corresponding y value is, and then find the slope of that tangent. Again, using the graph, another method that was discussed was to simply make a line that passes through that point there. Again, the way you would do this, if you want to be really professional, you would still go through this and then you'd figure out that your slope is something along the lines of that. So y is equals to negative, let's substitute that in, x. And then we would try to find out what our b value is. So our b value would be, if our value was 2.6 and negative and 3.74, let's put those on. 3.704 is equals to negative 4. Again, you don't have to go through this necessarily, but this is just to explain to you just how much work you need to do right now to get a precise answer compared to what I'm gonna show you tomorrow, which is gonna be so much more easier and a lot more exact. Again, just to finish this off, this could be plus x. Let's just find what x equals to. There you go. X is equals to 15.87. 15.871. There you go. That is what our beautiful tangent looks like on this graph. As you can see here, it's barely finding us an intersect point because it's actually super, super small. Again, there might be an issue of not exactly having the right slope, because at first we got negative 5, and negative 5 is all the way over there. Like, that doesn't make much sense. So again, you would try to make a line like this, and then you would anticipate, oh, okay, it looks like it crosses the value over here, which is 2.1 or 2.2, and then 5.6. So that would be your first x values, and then you have a point here, which is 3.2 and 1. So those would be your second point, and then you again find the slope that way. Again, this is more or less a review from last year, or whenever you took advanced functions, but it's still really, really important that you understand this, because as we move forward within the course, you will need the basics to understand the more advanced content we're going to be covering. Hopefully that little example helped you out to understand how we calculate the instantaneous rate of change for this subchapter. With that being said, that's all we had to cover. So this is the homework for today. It is 5 questions. 3 of them are pretty long. I'm not gonna lie, they're pretty long in terms of how many questions are given per question, but they don't take a lot of effort. They all deal with the same concept of trying to figure out delta y over delta x. For example, 8, I'll show you it right now, is this question here. As you can see, it has 4 different or 5 different parts to it, but it's also telling you trying to figure out what average rate of change is versus what instantaneous rate of change is. So it's almost like a true or false question. Again, this is just to test whether or not you understand the differences between AROC and IROC. Question 5 is really long, it's half a page, but it's also using very basic concepts like asking you what a dependent variable is versus what an independent variable is, just so you get into the mindset again of mathematics and how these terms can be used in applying to more difficult concepts. If you have any questions that you want me to take up, please leave a comment down below. I'll be happy to answer that for you, for example, in the next class. If everything is good, then we're going to be well off into chapter 1.2, which is actually dealing with rates of change using equations, which I'll tell you is a lot more difficult sounding than it really is. So if you enjoyed today's lesson, please let me know. I'd love to hear your feedback. Either way, I will see you next time, guys. So have a good one. Bye bye.